Good evening, Abhishek. Good evening, Niharika. Okay, let's start with the class then. Okay, so wishing you a very good evening, everyone. It is going to be the second session of the biomolecule chapter. So, as you already know in the previous class, I already give you a little bit brief about the structure, like how the structure look like and all these things. Okay, so kind of introduction part is already covered. And in order to observe the structure of the glucose, now we are going to check it about. That is the molecular formula part we already done. That is a C6H12 and O6 is there. Okay, now let's see that how to check it the presence of 6 carbon in the chain, presence of the carbonyl compound, presence of the CO group as a aldehyde, presence of 5 hydroxyl group, presence of primary alcoholic group, and the spatial arrangement of a OH group. So it means we are going to discuss one by one. So first of all, that how it was observed that is a glucose has total 6 carbon there. Okay. So let's try to understand this point. Okay, so sometime the question will like how to justify there's a 6 carbon present. So the point number one, that presence of 6 carbon chain. Okay, so let's see how that it's a CHO and then CH2OH. It's a 4 time, okay, and this is a CH2OH. So the structure part, I guess already you know because the previous class we discussed. In this, if I'm adding Hi, be noted. If you're using hydrogen iodide and heat it as well, so what we are end up with, we are end up with this hexane. Okay, so like all OH, oxygen, OH, every part simply reduces, and we are getting that is a CH3, CH2, 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 CH2 and CH3. So what is it? It's none. It's N hexane is there. Okay. So this is a proof number one that the presence of the 6 carbon in a chain. How to identify this? Just by simply using Hi as a reagent, and we are end up with a 6 member chain there, that is hexane, N hexane. Okay, proof number one. That's it. Now let's see how to check it. The next point, that is the presence of carbonyl group. Okay, so presence of carbonyl group. Now listen my point. If I want to check or you want to check the presence of carbonyl compound, so just go with the reaction with HCN. If you remember in the previous class we discussed about, let me give you a brief. If let's suppose this is a CO group, okay, carbonyl group, and if we are using HCN is there, so what is happening that one part is combined with cyanide and one part combined with OH is there. Okay, and then we used to call it a cyanohydrin. Okay, so this is how the cyanide or HCN is going to react with the carbonyl compound. Okay, so let's discuss the second point, that is the presence of the CO group there. So the presence of carbonyl group. Be noted, it's a CO group presence. It's not the aldehyde presence. So the presence of the carbonyl group. This is the second point. Okay. So in this case, if we are using glucose, so again that is a CHO, and every time we are using the same thing, it's a 4 time, and then CH2 and OH. And in this, if we are using NH2O4 is there. Okay, so what is it? It's a hydroxylamine. Okay, let me just write the name as well. So this given thing is hydroxyl amine. Okay, hydroxy word for the OH and amine for the NH2 part here. So what is happening that we are getting, let me just again brief this part as well. If you are having a CO group, okay, and we are using NH2OH is there. So what is happening? This carbon combined with this, and this is known, this thing is known as a oxime. Okay, so be noted. Like how in this case there's a water molecule removed. Okay, let me just write it be like this way. This is NH2, OH is there. So you can say from here the water molecule simply release and this NH going to combine with the double bond. So it's a oxime there. Okay, so this is how the reaction. HCN you can go, NH2 OH part you can go. So it means that this CO become like NOH. Okay, it will remain same. It is a CH2 and OH and it is a four time and then this is CH2 and OH is there. So if we are talking about the name, so what is the name? Like as I already told you on the previous slide, let me just back again. It's a oxime. Oxime, the name for this. So like glucose, so this become glucosine. That is glucose and oxime. So glucose is combined with the NH group, it's become oxime. So the point number one, the reaction with the hydroxylamine, let me just write as well, that reaction with hydroxylamine. This is a reaction number one just to check it the presence of the CO group. Okay. Now let's see the second reaction. Same like for checking the CO group that the reaction with HCN. Okay. So the reaction with HCN. Let's go again how the reaction is going on. Again, this is a CHO. It's a glucose molecule we're using again and again. And this is a CH2 and OH. And if I'm using HCN is there, so what we're getting that is a carbon. It's become OH and a cyanide part. Okay, just focus on the first carbon only. Okay, and then CH2OH. It's a four time, and this is a CH2 and OH. So this is how we are able to confirm that. Okay, uh, if let's write it's be like double bond and hydrogen. Okay, so it is confirmed now that this is a CO group and it is converted into the cyanohydrine part. So what is the name for this compound again? So it's a like hydrine part. So it's become gluco again. That is a glucocyanohydrine. Okay, you can take the reference from the previous one, cyanohydrine. Okay, so it's a cyanohydrine. These reaction we already covered in the carboxylic chapter if you remember. Okay, so this is how the reaction no, not the slide. Hmm, here, so this is the second point confirmed now that in glucose molecule there is just some CO group present. Okay, so two part just proved now. The point number one, how it is proved that is six carbon present in a glucose. This the reaction with HIV are end up with N-hexane. Okay, uh, wait. Okay, so I guess it's visible now, right? So then the second point, if we are talking that the CO presence there. Now let's see the third point, that is the presence of the aldehyde group. Okay, so let's just back again. The third point, that is the presence of the CO as a aldehyde. Okay, how to prove that it's a aldehyde there, right? So let's just talk about that point as well. That how to check it, is it aldehyde or ketone or what? Okay, so let's discuss about this. The third point, presence of CO as a aldehyde. This reaction is really important. Okay, it is a most commonly asked question in the previous years. That is how to check if the presence of CO as aldehyde. Okay, so let me just first write the theory, because theory is also important. So the theory said the presence of aldehyde group can be confirmed by oxidation with mild oxidizing agent. Okay, so now the question will like why I'm using mild oxidizing agent, because wait, I will tell you as well. If you remember the previous classes, so we are just start with the alcohol, and then if we are using oxidizing agent, then we are getting some kind of aldehyde, and then if further if oxidizing agent, then at the end we are with the acid there, right? So we already at the second point that we already have aldehyde, so just use mild oxidizing agent in order to get the acid there. Okay, So if we are talking about mild oxidizing agent, so you know the stronger one, HiO4, if you remember, HNO3. So those are the very strong oxidizing agent, right? But if I'm using only the bromine, bromine is a mild oxidizing agent. Bromine water does. Recall like that, okay? So it means mild one we are going to use. Yes. So let's see how the reaction look like. And again, it's very important reaction. So you can see reaction with bromine. Like this is a most commonly asked question that when the glucose react with the bromine, so what is the product we are getting? Name for this for the given acid is really important. Let me tell you how. So first of all, this is a CHO and it will remain same. This is 4 time. And the last one is CH2OH. Okay, and this is the bromine water. Okay. So what is happening? Only aldehyde is converted into the acid. Why? Because we are using a mild oxidizing agent. Next question, ma'am, why not strong? Because if you have to use the strong oxidizing agent, so OH is also present there, right? And you know very well that all alcohol is also going to convert into the acid there. So in order to remove this kind of misconception, we're using mild so that if aldehyde present, so automatically that is going to convert into the acid. Okay, so be noted, this is very important. I am repeating one more time. This is gluconic acid. It is gluconic acid that whenever the glucose is combined with the bromine. Okay, it's very, very much important. Gluconic acid. Only what is happening from there to there, that the CHO group simply converted to the COH group there. It's just oxidation of CHOH group there only. Okay, so the point number of, I guess, third, right? Gluconic acid. Yes, you're right, Ambika. Now, let's continue further. Now, let's see that right now we just proved 3 points that the presence of 6 carbon with the HI. Okay, presence of carbonyl group with HCN, or you can say with the one more, that is the oxime as well. Sorry, that is the hydroxyl amine as well. And then this group presence with the bromine. Now let's see how to prove that there's a 5 hydroxyl group also present there. Okay, so 5 hydroxyl group. So as I already told you, if you have to use the weak oxidizing agent, only aldehyde convert. But if we are using strong oxidizing agent, so all alcohol is going to convert it. So let's see what is happening then the next part. So the point number 4, presence of 5 OH group. Okay, so let's see how. Again, this is a CHO. Okay, so it is repeated part this, and in this case it is proved by, let me give you the how to prove this. This is just a theory by formation of, by the formation of derivative of, sorry, that is by the formation of penta acetyl derivative, penta acetyl derivative of glucose. How? I will tell you, just wait. Okay, so in this we are using anhydride. Okay, so which kind of anhydride we are using? CH3, CO and O, and CO and CH3. Okay, this reaction we discussed so many times. Let me tell you one more time quickly. Okay, so what was the reaction from the previous chapter, that if you are having alcohol and if you are using this Cl, or if you are using anhydride, or if you are using, I'm sorry, or if you're using let's say ester as well, that RCOOR is there. So what is happening, that this oxygen as a lone pair, it simply attack here and this bond open and this bond close and this is going to leave there. Okay, so it means ester formation take place there, esterification, this is known as esterification. So see this is how it's look like. Okay, so ester formation, and what does it, it's known as a acetyl. Okay, acetyl. So let's just back again, that if you are observing the 4 OH here and the 1 OH here. Okay, so just anhydride is present here and we are using 5 time of this, so this portion combined with every OH. So let me just write how it's look like. Okay, So that CO group, CHO will remain same. CHO is not going to be knotted. And then that CH part, okay, so it's a 4 times. So it's become COCH3. Okay, so like we are using 5 times. So one 4 time is already combined here, and this is a fifth time. So this is how we are proving the presence of total 5 oxygen there, and this is known as a glucose pentaacetate. Okay, acetate, ester formation is there. Look at this. This is the extra point, and see this. This is the next. So that's why total 5 molecule. So this just the presence of 5 OH group. Right now, whether the OH group is primary, secondary, it's not the point. Just only the presence. Okay. So in this previous table again, we discussed the proof till now. Look at this. Now let's see the next one. Presence of primary alcohol. Okay, there is a 5 alcohol, but which one is primary or which one is secondary? It is also important part, right? So let's just discuss about the presence of the primary alcohol as well. How many primary alcohol and how to prove this. Okay. Yes, Shiva. Let me just check. Maybe I missed some number then. Wait. Yes, it's a 4. Okay. My, oh, it's not like decent. Wait, I have to raise this. Okay, this. That is CH2OH. Is this point clear now? So you're right. Hmm. So, okay, let's just back again what we are discussing. That is the fifth point, the presence of the primary alcohol, right? Fifth point, presence of primary OH group. That how many primary alcohol is present, how to prove this. And again, like the bromine water, this is also a very much important reaction, okay? The name of the acid again. So let's see actually what is happening. That is, this is a CHO and this is CHOH and it is a 4 time and again it is a CH. Okay, got it. Like you are saying it how to be CH, right? I'm sorry. Okay, 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 Shiva. Okay, so maybe I use CH2. I'm sorry again. It's going to be the CH because otherwise the balance is disturbed, right? Okay, please correct this. Okay, it's right. Okay, then let's back. So this is CHNOH and this is CH2NOH. So presence. How to check it? That is, we have to use the strong oxidizing agent this time, that is HNO3. So HNO3 is not going to affect the secondary alcohol, only the primary. So look at this, primary alcohol and aldehyde both is going to oxidize further. So what is happening? This is a COH and the central part will remain same, that secondary alcohol is not going to affected by this, and this is a COH there. So before running the test for this the presence of the primary alcohol, it was already confirmed that aldehyde present. Because maybe this question arises, ma'am, isn't it the 2 time of COH? So it's secondary, sorry, primary alcohol. No, it's this part is already proved. That is one is a aldehyde. Okay, so it is confirmed now. What was the change? That this is a primary alcohol. It's become COH there. And again, the name of the acid is important. So what is the name of this acid? This is saccharic acid and it's really really important like the gluconic acid. Okay, it's a saccharic acid. Sometimes the problem be like saccharic or gluconic, which one is the correct answer? Okay, so if 2 CH group, so this is the answer. So it's proved now total. Let me quickly give you a brief that how to check it the presence of 6 carbon, the reaction with Hi, how to check it the presence of the carbonyl reaction with HCN or reaction with NH2OH is there, how to check it the presence of the aldehyde, that just reaction with bromine water, that mild oxidizing agent, that how to check the presence of 5OH group, reaction with anhydride, and we end up with the penta-acetyl group, and how to check it the presence of primary alcohol, reaction with HNO3, strong oxidizing agent, convert the primary alcohol into the acid as well, and we are end up with the saccharic acid. Yes, very good, Ambika. Okay, Okay, Shiva, got it. Okay, that's this is for fifth point. Now let's see the sixth one, that the stereochemistry as well, right? So let's talk about the last point, that is a spatial arrangement OH group. I guess it's six, right? So spatial arrangement, spatial arrangement of OH group. Okay then. So first of all, everyone, I guess you know, recall the Fisser projection. Okay, you know, Soho's Fisser projection. So what is the meaning of this Fisser projection? That when we're using these kind of line for just to draw a structure. Okay, so this is a Fisser projection. Haworth and Fisser one. So it's a Fisser one. So like here with whatever we are discussing right now, that are the Fisser projection and on the previous slide as well and here as well. Okay. So let me just write that what is the Fisser projection of the alcohol? This is a CHO. And in the previous class, I had told you that you have to write six carbon continuously. One carbon, two carbon, four and then five and then six. The last one that writes CH2OH. Okay, so every time that OH on the this side except the third carbon OH on the left side. Okay, otherwise on the right side. And hydrogen, 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 and hydrogen. This is just for understanding only. Okay, in the Fisser projection, actually, we are not using a carbon for the representation. Okay, so means what I want to tell you here, that instead of using this carbon, we have to just use a single straight line. Okay, so it's totally understood that in between the carbon is present here. Okay, so this is actually the Fisser projection. Okay, sometime if you are having a problem with this kind of structure, so always write total six carbon and then try to find out the structure there. So this is simple Fisser projection of the alcohol is there. Now this is also known as, okay, Fisser projection you can say, or the another name for the same thing is, or this is also known as a Fisser projection formula. Okay, so be noted, both are the same thing, Fisser projection or Fisser projection formula of glucose. Okay, so it's the same thing there. Anyway, let's talk about the spatial arrangement. Okay, so although I already told you in the previous class, let me quickly give you a brief. So if you're observing the last portion here, okay, I told you that for the second last carbon you have to check. Okay, for the second last carbon you have to check, and what is it? It is on the right hand side, and hence it become capital D. Okay, it become capital D if the OH present on the right hand side. So what is it? It's a D configuration, and in this case, if you're observing the OH part, okay, OH part, one OH, no, it's not that OH, one OH, two OH, three OH, and even the fourth as well. So that fourth OH present on a same side, and if you're observing the one only single OH that is present on the left hand side, right? So look at this, that is this is left hand side, this is right hand side I'm referring. So left hand only one OH, and on the right hand side total four OH is present there. Okay, now glucose can be dextrorotatory, glucose can be levorotatory. Okay, but right now that in the chain structure we are not able to identify is it dextrorotatory or is it levorotatory. Okay, just wait, I will tell you what I want to explain to you. Okay, so first of all, let me quickly give you a brief about the dextro and levorotatory. Okay, and the I guess in the previous class I told you about this point if I remember. Yes, I guess yes. So that is what is dextrorotatory. For example, if this, let's suppose this is a dial, you know, this is a polarimeter. Okay, so it's a kind of telescope when you are using your eye on the eyepiece. So there is some deflection. There's a zero is the degree Celsius scale, and then this side that is a 1 degree, 2 degree, 3 degree, 4 degree, and up to so on. Okay, so all are the positive value you can say. Maybe you already know the vernier caliper. Okay, so there's a some kind of scale there, so same here. And then same this side, that is the negative, that is a -1 degree. Okay, let's say that 10 degree. Okay, because the list count is not that much small. Okay, 40 degree, let's say. And this side that is -20, this side that is -30, and this side that is -40 there. Okay, so let's suppose some light come. Okay, plain polarized light simply. Okay, so when it transfer here, so if the given compound is dextrorotatory, so according to the rotation, that this side we are having a direction. So what is it? That is positive direction. And which direction? How the this is how the clock moving, clockwise direction. So it is a clockwise direction. Clockwise direction. Similarly, that if we are observing this side, so it's a negative direction. And which direction? It is anti-clockwise. Okay, so it's a anti-clockwise. So if anti-clockwise, it become levorotatory, and if clockwise, it's become dextrorotatory. Okay, so this is how we are able to decide. But here in this chapter, like obviously we are not having any light, so be noted that if the OH group if the OH group present on the right hand side, right clockwise, clock is always right. And then if OH present on the left hand side, so it's become levo. So right hand side dextrorotatory and left hand side it become levorotatory. I will tell you now why that which OH you are going to check, because maybe you'll be like, ma'am, see, so four OH on the right hand side and one OH on the left side. So is it dextrorotatory or levorotatory? Okay, we are going to cover this point as well. First of all, yes, you're right, Abhishek. Okay, first of all, let me just quickly finish about the structure is there, and then we are going to discuss that part as well. Okay, now, so after this, all discovering all the point that six carbon, everything is present. Okay, there is a problem with this. What was the problem? That this spatial arrangement, or you can say open chain structure, was not able to give some test. If you remember, if the CO group is present there, so yes, it does give the reaction with this NaHSO3, sodium hydrogen sulfide. Okay, if that carbonyl group is present, it is also give you the test positive with the CIF base. Okay, CIF reagent test, if you remember. Okay, but the problem was what was the problem at that point of time? That these tests are negative. It means there is a no reaction. Okay, so like what was the problem? That we just prove it's like six carbon and CO group every point. But question be like, why not the test positive for the CIF reagent or the NaHCO3? Okay, so no justification there. So some be like CO group present, some be like no, CO group is not present. Okay, now a new point came into the picture. Do you know actually glucose is not a straight chain? Okay, it's not a straight chain. This is actually a cyclic structure. Okay, so cyclic structure means what do you want to explain? We are not getting anything. So listen my point that according to all the rule and regulation, it is a straight chain. Okay, but what was the problem? That still there is a some test like that test with CIF reagent or NaCSO3 test is not positive. Okay, then what was the problem with the structure? So then some scientists come and they be like, no, it's a cyclic structure. So it's a cyclic structure. So now everyone start proving that it's a cyclic structure. So means what is the meaning of this word cyclic structure? Let's try to understand. And yes, in reality, cyclic structure of glucose exit the single or the straight chain structure is not really exist. We will cover that point as well, that ma'am how the test positive if it is not a straight line. Okay, so actually the concept will be in the upcoming classes is a muta rotation. Okay, if we are having time, so we are going to finish in the today's class only, right? So let me tell you that first of all, how to draw the cyclic structure. The biggest problem to draw the cyclic structures. Okay, so let's more discuss about the cyclic structure, that how really that is a cyclic structure look like. Okay, again, first of all, draw the straight line. Okay, so this is a C OH group, hydrogen, carbon, OH this side, hydrogen, carbon, OH this side, hydrogen, carbon, OH this side, and hydrogen. 1 2 3 4, one more carbon, that is OH and hydrogen, and this is CH2 and OH. Okay, so actually how the structure is there, that count the number of carbon: 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbon, fifth carbon. Okay, fifth carbon OH. Listen my point. That is a fifth carbon OH group simply combined with the first CO there. Okay, this is how the bond open up. And and really how the structure look like. Okay, it's equilibrium reaction. How the structure look like, you can see the carbon number one. Okay, and carbon. Okay, just for understanding purpose, I am simply omitting all the OH right now. Okay, so just try to understand. That is this carbon and the first carbon form a bond with one another. Okay, and this bond opener, if you remember, acetyl and ketyl part, quickly let me give you. That is, if you are having a double bond and if you are using some ROH group is there, so what is happening, that the R formation is there and one is the OH group, right? It is known as a hemi acetyl. If you are using aldehyde, if you are using ketones, become ketyl. Okay, and if let's suppose I'm using a 2 mole of this, so it's become OR, and this is the case. So it's a normal, it is a acetal. Okay, now here we are under with the hemiacetal. Okay, let me just back again. So it means this OH combine, this carbon combined with one OH group. Okay, so one OH group. So let's restore all the hydrogen. So this is hydrogen. Okay, everything will remain same, they are not going to change. So it's a OH, it is a hydrogen, and OH, OH, hydrogen, and the last group will remain same, that is a COH is there. Okay, now look at the carbon number one, this carbon. Now this carbon is going to decide, that is the glucose is dextrorotatory or levorotatory. Okay, so let's see how to identify. So let's understand this. Okay, now in this case, uh, wait, let me quickly give you a brief. If this is a CO group and some nucleophile come into the picture, maybe nucleophile attack above the plane, maybe nucleophile attack below the plane. So both possibility can be there, maybe OH above or the nucleophile below, or the condition number two, maybe nucleophile above and OH below there, right? So same here, that is maybe the OH above the plane or maybe OH below the plane. Okay, so this is cyclic structure of the glucose, but it can be different on the basis of the stereochemistry. So let's see how it's really look like. So the point number one, the carbon number one, maybe the OH present on this side. Okay, this is carbon number one be noted. Okay, and the second will remain same. Then you can directly go like which we already covered. Okay, third carbon. Just make this thing very clear. Only third carbon has a different kind of arrangement of OH group. So four carbon done, right? And this is O and hydrogen, and this is a CH2 and OH. Okay, look at this. Or the second point, even you can change the position of this thing. Okay, it's not like I'm using like that way. So you have to do. And in between, open chain structure. Okay, so now ready. Look at this. This side, OH on the right side. So it's a alpha D positive glucose. Okay, so alpha, it means the OH on the right hand side, and it is going to rotate the direction or the plane polarized into the right direction. So positive means for the dextrorotatory. Okay, and this is OH, so it's a left hand side, so it's become beta. Beta D positive glucose one more time. So this is how we are going to observe the naming. Okay, Shiva, that is this is just a structure only. Okay, wait, I am changing the position of my video. Okay, look at this. So this is how the cyclic structure form. Okay, this is just a way to form a cyclic structure. Okay, now maybe this question again the the question come that ma'am, why only the fifth one? Okay, sure. So let's count the member in a ring. Okay, so let's start. That is a member number one. One, two, three, four, five, six. So it is a six-member ring. Okay, wait. When we are discussing fully about the structure, okay, this is just a kind like how to understand this. Wait, I will give you a kind of other structure as well. Pyrene and purine, then you maybe you will get my point. Okay, so is this point clear now? Now observe this, that the carbon number one, right? So in this case, what is happening there, that is a C1, carbon number one. Let me just put a star. That is a carbon number one. Both have a different arrangement. Okay, only I'm repeating again that only the carbon number one has a different kind of arrangement in a space here. Carbon number one, and this kind of arrangement when two structure has a different configuration with respect to the first carbon is known as a anomeric carbon. Okay, anomeric carbon, that when the first carbon is differ in position. I will tell you the definition as well, just try to observe this. Okay, let's wait for some time. Okay, maybe some point is not clear at your ma'am, what is this? Okay, can't other OH attack on a COH? Okay, Shiva. Okay, I will take. Okay, just wait. As I already told you, that some point not very clear at your end, but ma'am, what you are doing? Wait for some time. Every point will be decoded soon. Okay, anomeric carbon. So the carbon number one differ in configuration. So this is known as an anomeric carbon. Okay, so let me give you the definition for this anomeric carbon now. So what is anomeric carbon? Because we are going to use two things here. One is that is the epimer, one is the anomer is there. Okay, so that's why I'm explaining this thing to you. Okay, so what is anomer? What is anomers, right? So write the definition: two cyclic hemiacetal. Okay, I guess this point is very much clear why the name is hemiacetal. I already told you. Okay, see, this is not the slide. Where was the slide? Okay, maybe we already covered hemiacetal part. Okay, so it's not fully acetal because only one part, one portion become the ester is there. Okay, so that's why I said ester. I'm sorry, ether. So two cyclic hemiacetal form of glucose differ only in configuration of hydroxyl group at C1 position is called anomeric carbon. Okay, if let's suppose in paper you don't know like two cyclic hemiacetal, just be noted two different form of glucose which are different in configuration at first carbon only. It's enough. It's enough for the definition for anomers. Okay, so example, if we are discussing about the example here, so you can say alpha and beta glucose are the example of anomeric carbons. Okay, this is example. Okay, that's it. Now, okay, let's just back again. So it's very weird kind of structure, right? That it's not very much clear what I really want to give you. Okay, so now we are going to represent this thing into two form. Okay, so the point number one, it's going to be the pyrenes, or the second one, it's going to be the furane. Okay, don't worry, we will cover every point. So let's just first discuss about, I said furane and pyrene. Okay, so what is this pyrenose or this? Okay, so let's discuss more about the cyclic structure of glucose. Okay, so cyclic structure of glucose. So first of all, write some statement. Okay, so alpha and beta Alpha and beta form of glucose can be represented in form of six membering. Okay, because we know from the Bayes chain theory that a six membering is much more stable over five and seven is there. Okay, so membering called as, it was as, so as pyranose structure. Okay, so let's see actually how it's look like. That is how the pyramid look like. So this is a oxygen fit, and this is a six membering like this. Okay, double bond. So actually this is pyrene. So means whatever be the structure we just discuss actually look like in this way as well. So it's a pyrene. So this kind of structure is known as pyranose. Pyranose structure of glucose. Okay. So let's see if you're observing something, one more thing, that there is a total five carbon. Look at this structure only. Okay. So in this case, what is happening? Total five carbon and one oxygen, right? One oxygen. So six member total, five carbon, one oxygen. Okay. So now let me again draw the previous structure. Let's quickly draw one carbon, two, three, four, five, and six. Just try to understand this point. Everything otherwise is very easy. Just wait for some time. Which, okay, that's it. Now, this structure, let me tell you how. So it means we are actually rotating the structure like this, okay, like this way. So try to understand. First, draw the six member, everyone. Okay, structure is very important. Okay, you try to draw with me. I'm repeating one more time. Draw a six member. Let me form one more time. That is a six member. Okay, six member. And just put the oxygen here, right? According to the concept, the oxygen connected with which carbon? Okay, look at this. It's a first carbon, right? One carbon, two carbon, three carbon, four carbon, five carbon, six carbon. This is my first carbon. This is my second carbon, third carbon, fourth carbon, fifth carbon. Okay, you'll be like, Mom, where's the sixth carbon? Wait. Okay, so now look at this first carbon. Let me highlight. This is my first carbon. So first carbon. Be noted that whatever we present on right hand side, you have to put down. Okay, try to understand that this is the structure and we are just tilting B like this way. It means after once you have to rotate, our OH look like this way. Okay, so the carbon number one hydrogen, the carbon number two OH and H, and the third carbon look like OH and H. Okay, so let me just give the number again. Like first carbon, second carbon, and third carbon. So third carbon is above. Okay, so you can say right hand side that you have to put above the plane, or what will be right hand side that is you have to put below the plane. Okay, below, left side above, or right side below. So just tilt it like this way. Okay, so just try to understand. I will repeat one more time if you're not getting. Okay, so the carbon number one. Okay, carbon number one, noting something that this OH right hand side, so below the plane OH, first carbon, focus on first carbon only. Now let's see the second carbon. Again, hydrogen above and OH below, third carbon. Because the third is the only exception here, OH above and hydrogen below. Okay, fourth carbon, that is again our hydrogen above and OH below. Fifth carbon. Okay, fifth carbon, that this CH2OH above and hydrogen below. Okay, so this is the structure is ready, and this type of structure is known as a pyranose structure. Okay, it's a pyranose structure of glucose. Okay, observe for some time. Take your time. If not getting, I will repeat one more time. Structure part is clear. How to draw the structure? If not clear, let me know. I will repeat one more time because it's really important. Okay, so is this point clear now, Shiva? That why only fifth carbon? Because we are end up with a six member ring. If you have to go with fourth carbon, the resulting ring total is five member. If you have to go with the third, so it's four. Okay, so that's why only fifth carbon form a probable, the correct one, six member ring with the first carbon. Okay. Yes, please. Any problem with the structure? Is this point clear how to draw or not? In the biochemistry, the glucose structure is the only thing, okay? Otherwise, everything is just a theory only. I guess it's clear. So, okay, good. So, what is it? It's a alpha form, okay? So, now you can differentiate even. Look at this. That is the first carbon, OH, right hand side. So, OH, that is a below. So, it's what? That is just go with the second, first carbon only. It's a alpha. It's a alpha D glucose. Okay, so it's a alpha D glucose there. Ma'am, if I want to draw the beta D, just everything will remain same. Okay, only what is happening? That is the first carbon is differ. Okay, let me draw the beta D as well. Okay, so again, I know the structure. Okay, soon you will be habitual as well. So now only first carbon is different, which above the plane. So hydrogen, and then this is OH, OH. Okay, see this. So one carbon above, right? So above means remember right hand side. So right hand side, which levorotatory, right? So it's become beta D glucose. Okay, so it's a beta D glucose here. So the previous one is the alpha, and this is a beta D glucose. Okay, so that's it. That's this is the only thing we are going to remember from here, the structure part. So alpha or beta. Okay, this is the form number one. Okay, now sometime you also end up with this kind of structure as well. Okay, remember everyone? Okay, I know so many things, but still try to understand. If the question asks about beta, okay, I'm giving you a trick. Okay, just quickly how to identify if the given thing is beta or alpha. Because I know the problem with the student, like, ma'am, alpha, beta, it takes so much time. So be noted, if you are checking for beta, so be noted every OH is equatorial position. It's a trick. In beta D glucose, every OH should be at that equatorial position. So, for example, that OH equatorial, okay, and in this case, OH equatorial, OH equatorial, OH equatorial, OH equatorial. So, this is beta D glucose, okay. I'm sorry, CH2OH. Okay, so this is simple beta D glucose, capital D, right? And what if it is alpha? So alpha only first carbon one axial. Okay, so this is how you can quickly identify, and it is easy to remember as compared to the previous one. Okay, as compared to this, where was the structure as compared to this? So if you are not able to remember the previous one, just go with this. Both are the same. Okay, because you know a very well six member cyclic structure actually look like a chair form, and chair conform is the much more stable one. Okay, most of the time in book you're observing this kind of structure as compared to the previous one. So what I am explaining to you, that is only first carbon has a D for OH, otherwise everyone be like equatorial. So OH, okay, maybe some time you are having issue with the axial and equatorial, right? So you know the straight chain, axial, 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 axial. So this is axial position again, equatorial, okay, axial, 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 axial. So this is actually how the cyclic structure look like. Okay, so two type of structure. Okay, Arul, listen my point. If you don't know the difference, in the previous class I told you that is you to check it for last second carbon. Okay, so like in this case, this is CH2OH. If the last second carbon, the OH present on this side, right hand side, so it is a capital D. Okay, if the last second carbon present on this side, so it's a capital L. Okay, so this is the configuration simply that decide the which direction there. Okay, is this point clear? And what is small d? Dextrorotatory, Arul, that the direction of the light, plain polarized light when passing through a polarimeter. So the direction, if the scale is moving toward the clockwise direction, so it's become dextrorotatory, positive direction. If left hand side levorotated, it means negative direction. Okay, and the second thing we discuss here, alpha and beta. Okay, so what is the meaning of alpha and beta? That is if the first carbon OH present on the right hand side, so it's alpha. I said first carbon, carbon number one. Okay, and if the OH present on the left hand side, so it's become beta there. Okay, so 2 point we discuss, D or L, or alpha and beta. Okay, so let's just back again. Observe this. So in this case, OH this side, so it's become right side. And what is this? It's a alpha form, alpha, and capital D, for the capital D rule, we are checking the last second carbon, the OH this side. Okay, right now this is participating in a ring, but it's a right hand side, so capital D plus for dextrorotary, is glucose for glucose. Okay, yes, please let me know now, is this point clear now? Okay, so this is also known as, if we are using a name here, so this is also known as like, maybe, okay, you will like, ma'am, you taught it differently. So sometime in a book the name be like glucopyranose. Okay, so be noted, they are just referring this kind of structure, this pyranose structure. Okay, so this is all for the pyranose structure of the glucose there. Okay, so now next, there's a twist in a story one more time. Remember in the previous class we discussed about reducing and non-reducing sugar, everyone. But the miracle be like, ma'am, you just told us the cyclic structure is the actually exist in the nature, and the open chain is not really exist. So my question to you, that how to justify that it is a reducing say sugar and it reduces the tolerant and the failing solution? Yes, please. Okay, I'm repeating my question. In the last class, we discussed about a classification. Alpha. Alpha means that the first carbon rule, anomeric carbon, differ in configuration. Okay, so if alpha means OH on the right hand side, beta means OH on the left hand side. Okay, so this is just a kind of configurations. Actually, I guess we not covered about the stereochemistry, right? Yes, please. Anyone? How to justify Toller and Failing test positive if CO, actually LDH is not present here? Yes, please. Anyone? Do you know the reason that why still they are giving the Toller and Failing test positive? Come on, everything connected with the previous class. Okay, so what we just discussed in cyclic structure, hemiacetal, right? The CO group, just observe one more time. The CO group form a hemiacetal, right? So, if you recall the previous classes, in the previous classes we discussed about, that is Tolan test or Fehling test is given positive by hemiacetal as well. Why? Because after the tautomerism, OH can form the aldehyde as well. So hemiacetal give the test positive, but we are talking about acetal only, so no test positive. Okay, so it means the presence of the OH, the presence of the free OH group on the first carbon is responsible for the reducing sugar. when we are discussing about the structure of the sucrose, then you will get my point that why I just told you about the presence of OH group at the first carbon. So be noted that if the first carbon OH is free, so it is a reducing sugar. If the first carbon OH is not free, so it's a non-reducing sugar. These things we come to know after once we are discussing about the structures there. Okay, so this is a basic structure, this is a basic point, and now we are going moving further there. Okay, so this is justify that how the test for the like other thing is positive. Okay, now let's just back here. So now collect all the information. In the first part of the class, we discussed that how open chain structure look like. Okay, we discussed so many tests like test with HI, test with brom in water, test with HNO3. And you'll be like, ma'am, you just told us that it's a ring there. So it's isn't it controversy? Sometimes we're saying cyclic, sometimes we're saying that is the ring there. So now a new concept come. Do you know? Yes, all three form alpha, beta, and open chain present at equilibrium position. And this is one of the famous phenomena that is muta rotation. Okay, so let's just first discuss about the muta rotation and then we're going to discuss about one more important point. So it's a muta rotation. So what is the meaning of beta rotation? That some test give us that glucose is a open chain. Some tests justify no, glucose is a straight chain. Okay, then scientists be like, wait, all are present in equilibrium. So what is muta rotation? First of all, let's write the definition, and you can say that muta rotation is heart and soul of this chapter. Very, really important topic. From the board exam point of view, every time you are expecting the question from the muta rotation. So it's a really, really, really very much important topic. Okay, so let's write the theory first, okay? Then I will give you the concept as well. So when a crystal, just definition point of view. So what is muta rotation? When crystal, you know, let's suppose this is a box and put some crystal of the sugar. So what is happening? The crystal of a pure alpha D glucose are dissolved in water. Generally, in laboratory, alpha D glucose present. This is the most abundant form of the glucose. We discussed, I guess, in the previous class already. Okay, so dissolved in water. So when alpha D glucose dissolve in water, okay, so the specific rotation gradually. You know what is the meaning of this? That like a gradation in a decrease or increase. Okay, it's not like quickly or no, it's a very slow reaction you can say. So gradually changes step by step from plus 112 to 2 to plus 52.7. Yes, you have to remember the rotation. 112 to 52.7. Rotation change. Okay, what is the meaning of rotation? Let's suppose this is a scale. Okay, I already told you the scale and it is 0. So in the first one, the rotation is 112. Okay, plus 112. Now if you are adding into the water, so rotation little bit change. And let's suppose now the new scale here, that is 57.2 there. Okay, so rotation change. Okay, simply something happening, that's why the rotation change. We will cover, wait. Okay, so when alpha D glucose are dissolving in water. Okay, then second one, it's a statement number one, point number one, you can say. Second point. Then we be like, what if beta D glucose form? Okay, sorry, added into the water. So next point, that is when crystal of beta D glucose. Actually, I'm habitual about the small d. So beta D glucose are dissolved in water. The specific rotation gradually changes from plus 18.7 to plus 52.7. Okay, so the point to be noted here, that if you're observing, look at this, 112 112 become to 52.7, and 18.7 become 52.7. Okay, so it means be like at 52 52.7 something is present there, because every time the rotation stop here only, right? So what does it actually? So you can say you have to start some point A. Okay, let me just give you a quick brief actually what is happening. Okay, so there's a some point number A. So there's a some point number A. You are starting with plus 18. There's a some point number B. You are starting with plus 12.2. Okay, and okay, just use some point weight, and then they are end up with a center. Okay, and center is 52.7 there. Okay, so there's a B, and that is the point is 52.7. Okay, so what do you mean by this word? Think about it. We have to start with some A and some B, and at the end we are end up with a single point. So in term of chemistry, it is equilibrium condition, right? You have to start with some A, some B, and after some time, equilibrium achieve, and both are at a same type, the same concentration there, same concentrations you can say, or constant change in a concentration you can say. So it means that from this experiment, we come to know alpha and beta actually present at equilibrium with one another, the point number one. Okay, so let's see actually what is muta rotation. And you know that 52 point, that this open chain. So let me just write that how the structure is there. I'm doing nothing, just simply drawing the structures only. Can you just tell me the okay, this one, is this alpha or beta? And if you're not using hydrogen, so be noted it's will be like they already present. Okay. Yes. Alpha or beta. Yes, Ambika, it's alpha form, right? So in this case, if you're observing that, recall right hand side down, okay? So OH present down, and here OH present above there. So it's alpha, and the previous one, next one is beta there. Okay, then so let's write the name here. So it is alpha D glucose. Okay, it's a beta D glucose. It is 63% abundance wise, and it is 64% at equilibrium, and it is 0.02% at equilibrium, and all structure are just equilibrium with one another. Okay, so again observe this, alpha form, beta form, and open chain, all three are at equilibrium with one another. Okay, for this one the rotation is that 112.7, and for this the rotation is sorry, 18.7. Okay, 18.7, and for this one 52.7. Okay, it's 2 there. It's easy to remember. How to remember? Like I used to remember, it's a rhyme: 7 7, 18.7, 52.7, 52 point 112.2 there. Okay, so this is how you can remember. Here rotation is really important, the number is also important, all are the plus, it's a plus, it's a plus, it's a plus as well. Okay, so this open chain is actually equilibrium between both the closed chain there. Okay, so why, some test was not positive, like the reaction with NHSO3, rather reaction with the SIP base, because it's 0.02% only. So if we are discussing about some reaction which was not given positive by the open chain, the reason was that 0.02% is a very small point amount as compared to this 36% and 64%, and hence that the really open chain is just a very small amount. Yes, it is present, but in a very small amount. Okay, so this is meta rotation and it's important topic. No, it's 36. Okay. I use 63. I'm sorry, okay? Even you can balance. It's 36%. Okay, it's 64%. Total have to be 100%. And this is just a trace that is 0.02%. Okay, who's asking? Ampika. Is this point clear now? This is all for the case. Now let's see the last topic of the class, that is epimer. Okay, so first part, anomer, alpha beta form, first carbon different configuration. Now let's see the second type, that is epimer. So what is the meaning of epimer? Here two important point, anomer and epimer. Okay, only. So what is epimer? First definition. So what is the definition said? Two monosaccharide. It means simple. We just discussed right now is monosaccharide only. So two monosaccharides differ in configuration, differ in configuration of OH group, of OH group at any carbon atom called apimer. Okay, listen my point. Other than the first carbon, if first carbon differ, so that become anomer. If another at like first, second carbon, third carbon, fourth carbon, fifth carbon, any carbon other than the first, known as apimer. For example, let's try to understand this point as well. For example, what is the meaning of apimer? Let's discuss about this is a CO, hydrogen, OH, hydrogen, OH. So it's a glucose, okay? OH and hydrogen. This is CH2 and OH. This is CO, hydrogen, hydrogen, OH. Okay, look at both the structure here. If you're observing something, let me highlight this point. Okay, this point and this point. All are same. Look at this. Here, the OH present on this side and here OH is here. You can count the number as well. It's a 1 carbon, 2, 3, 4, 5, 6. It's a 1, 2, 3, 4, 5, and 6. So at third carbon the configuration is different. Okay, so they are the example of epimer. Okay, both are the example of epimer. Okay, now, and this is known as a C3 epimer. C3 epimer. It means that is the epimer at the third carbon here. Okay, that's it. Okay, this is all for the epimer. Done. This is all for the theory now. Now you're done. Any problem or any doubt? Okay, please revise the biomolecule chapter properly. It is not easy chapter. Okay, because theory and plus structure and so many things. Okay, yes, please. Now you're done. Any doubt, any problem? Okay then. So thank you so much then. Okay, thanks for joining the class, and now we can leave the class. Thank you so much. Have a nice day, everyone. Thank you. Welcome, Ambika. Thank you so much, everyone.